You know that feeling, that universal human experience of driving down a busy street trying to find a parallel parking spot?
Hmm.
And you see this huge gap, but then you realize no matter how you try, it's too small.
Because the cars on either side have left these two small, just completely useless, awkward bits of pavement.
Exactly. And that everyday frustration, it actually lands us right in the middle of a really profound mathematical puzzle.
It does. Today, we're doing a deep dive into Alfred Rényi's classical parking problem, which he first posed all the way back in 1958.
And the thought experiment is really about this. If
Yeah.
you place things purely at random, how much space do you just have to waste?
The challenge is deceptively simple.
Hmm.
Imagine you have a street of length, $6. How many cars, we'll call them unit-length cars, can you expect to fit if every placement is chosen randomly?
And if an attempt overlaps a car that's already there, it's just rejected.
Right. And the process stops when you can't fit any more cars in. That's what we call the
Mm.
jamming limit.
So here's the key. Why is this seemingly simple geometric limit from, the 50s? Why is it dictating how the most advanced generative AI works today? That's what we need to unpack.
Okay, so Rényi's solution revealed a really critical finding. As the street length, $6 goes to infinity.
On a very, very long street.
Exactly.
Yeah.
The mean density of cars, so the occupied space divided by the total length, it approaches a specific constant. We call it $6.
Rennie's parking constant. And the value is about,
It's approximately 0.7475979.
so just under 75%.
That's right. What that number tells you is that in any system where you place things sequentially and randomly, you can only ever fill about 74.76% of the space.
And the other 25% is just gone.
It's geometric waste. It's baked into the randomness of the process itself.
So that inefficiency is a fundamental mathematical truth of random packing. It's an absolute ceiling. Okay, before we bridge this gap from 1958 geometry to modern AI, just want to take a quick moment for our sponsor. If you are looking to uncover where agents could make the most impact for your business or personal life, or maybe you need help with AI training, automation, or software development, check out embersilk.com for your AI needs. They really can help you navigate that complexity. Okay, so generative AI. Let's make the connection.
The connection is surprisingly direct. The dynamics of that random space filling are mathematically analogous to how tokens work in transformer architectures.
In things like large language models.
Exactly. The key is something called causal attention masking.
Right. I know tokens are like units of context, but how does the model enforce that no overlap rule we saw with the cars?
That's what the causal mask does. It makes sure tokens are processed in a strict sequence. A token can only look backward at the context that has already been placed.
So it can't see into the future. It can't use info from tokens that come later.
Precisely. It mirrors that one-way, sequential, non-overlapping placement of the cars on the street.
Got it. So the tokens are like these interacting particles, but they're not on a street. They're in some high-dimensional vector space. If the model is doing this random packing, how does it manage to focus on context efficiently?
That's where the Rényi centers come in. This is the model's efficiency hack.
Rényi centers.
Yes. Research has identified certain tokens that achieve enough separation from others. They become these metastable anchors.
Meaning what exactly?
Meaning the model has figured out that these are the core, well-separated points of context. Because they're stable and, non-overlapping, the network can use them as foundational reference points. It reduces the need to process every single token in between.
That is a beautiful insight. A constant that describes inefficient parallel parking is actually telling us how to achieve maximum computational efficiency.
That's it. That 74.76% limit informs us how densely context can realistically be packed and accessed inside the network.
And that's all for a one-dimensional problem.
Absolutely. And this is where it gets even more exciting. The two-dimensional variant, so trying to pack squares or circles randomly, is much, much harder. The density limit is still an open question. There's a conjecture, but it seems to be wrong.
So that raises a fascinating thought for you to take away. If cracking the one-dimensional limit helped us understand language and sequence processing, could solving the higher dimensional jamming limit for simple 2D shapes unlock even greater efficiency in future multimodal AI, things that deal with images and video? The math that drives efficiency is still being written. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.